Thank you very much. So I get a head start. I'm going to tell you about attempts to derive gravity from CFT and from quantum field theory. And this is an ongoing effort over the last few years involving many people, a lot of papers that aren't me, but the people that I've been working with on this are written here. So let me start with a few words of motivation. We know that ADS-CFT is true. We know that gravity in ADS can be viewed as emerging from a strongly coupled quantum field theory, conformal invariance. But despite the many checks and confirmations we have of this, we still really don't understand a lot of the very basic questions you'd like to understand about emergent geometry. We don't really understand how it works. So if we understood how it works, then we could just derive gravity from quantum field theory. Okay, but we don't know how that goes. We don't know how it is that the collective dynamics of some strongly interacting system produce a geometry. So where is that geometry coming from? Partly because we don't know how to calculate things very well in strongly coupled QFT.
But not only because of that.
Right, not only because of that. It's right.
In large N vector theories, we can calculate everything we want, and yet nobody's really managed to get that.
That's right. Yeah, exactly. Well, I think, maybe it's because of that. I mean, maybe if we really knew how to calculate things in the best possible way, the geometry would come out automatically. It's hard to say in advance. What I mean by this is we know some supersymmetric examples where ADS-CFT is true, but presumably it's true in some large universality class of theories.
Sorry, I just one more thing. In the old matrix models, the matrix models are completely solvable. String theory is completely solvable. And we know the dictionary between them, these leg pole factors, and yet we don't know why it's right. I mean, so my take from that is that we can calculate everything you want to calculate, and you still don't understand.
Maybe it wasn't done in the best possible way yet. I don't know. Yeah, no, I agree. Yeah. So what defines this universality class of holographic theories? The kinds of questions that we would like to be able to ask are, like, what is the landscape of possible quantum gravities in ADS? I don't know if that means there are just a few or that we're supposed to list them. I'm not even sure exactly what the question is, but we'd like to know how to approach that. What are the properties that are common to all theories of quantum gravity in ADS? Do they all have strings? Do they all have extra dimensions? These are things that we should be able to answer because they're just statements. They're just questions about CFT. If we really knew how to do this right, we could answer the question of whether there are theories of quantum gravity in ADS3 without strings. Maybe we could even construct them. Does the swampland exist? Okay, so the swampland, this I think is, well, swampland means many things, but it's basically the idea that there are infrared theories that don't come from quantum gravity. And if we're ever going to make predictions for observable physics from quantum gravity, this is really a key question. It's whether knowing about consistency in the UV, we can really say anything at all about the infrared. And despite all the discussion of the swampland, I think that there's not really convincing evidence at this point that there is such thing as a swampland. We don't know whether there are consistent infrared theories that can't be coupled to gravity. That's another thing that we should be able to answer using ADS-CFT. Where? What I'm getting at there is we don't understand locality very well in ADS-CFT. We don't understand how to describe things deep inside the bulk, especially things that are behind a horizon. We don't understand how string theory evades the information paradox, which seems to be a question of locality. these are all kind of big open questions. What I'm going to discuss in these lectures is a small piece of this, which is basically the goal is to understand how far we can get with deriving gravity directly from quantum field theory. So that's the goal. The way I've written it here is the goal is to use holography as a guide to build a toolkit for interacting quantum field theory. And there's really two motivations for doing that. One is just because we need to better understand strongly interacting quantum field theory. So you can, if you can do this, then you can imagine applications to strongly correlated matter. In this point of view, holography or gravity is like the mathematical trick, and quantum field theory is the target. It could be that we can just use black holes and holography to get better at doing quantum field theory, and that's part of the goal. It's just to get better at doing quantum field theory without gravity and apply that to interacting matter. But the other goal is to go the other way and to use this to understand emergent geometry. And well, this is the goal that I'm more excited about. I mean, they're both good things to learn about. But here, what I have in mind is that if we can understand where the geometry is coming from first principles, directly from quantum field theory, then we can just study quantum field theory until we can start to answer some of these questions. Okay, so that's what I mean by, it goes both ways. First, we want to use holography to better understand quantum field theory, and then once we understand how the map works, we want to take what we've learned and go back and start mapping out the possibilities for quantum gravity and ADS. Okay, so in these lectures, I'm going to give, as I said, sort of a overview of some of the things that we know about deriving gravity from quantum field theory. A recurring theme, or maybe a key point that I'll make in various ways, is that CFTs with a large number of degrees of freedom and sparse spectrum, I'll define this in detail later, but this just means that there aren't too many light operators are in one-to-one correspondence or responsible for emergent geometry, and that this mapping between the two can be made very explicit using techniques from the Bootstrap. So Bootstrap can mean many different things. By Bootstrap, I guess my working definition of Bootstrap here is just that I mean by studying the operator content of quantum field theories without reference to the Lagrangian, using general methods just based on consistency, unitarity, and symmetries. So that's what I mean. And my point is that at least in a lot of situations that we can understand with the right tools, this duality between these two is not really, or can be demystified. That you can make this map very explicit and derive the infrared gravity dual from the quantum field theory. Although I'll also try to highlight the many places where we don't know how to do this and still need to figure out how this works. Ultimately, ultimately that's where I would like to go with this program, but right now, no, not really. I think that at least understanding interacting CFTs deformed by relevant operators, if you really understand how to do this, that's a natural next step to start turning on those operators.
Sorry, just to understand what you said here. So to show that a CFT with large number of degrees of freedom and sparse spectrum. So would the claim be that all CFTs with large number of degrees of freedom and a suitably defined notion of sparse spectrum will lead to smooth emergent geometry?
I would say that yes, but that part of this program is understanding exactly what's meant by sparse spectrum and pinning down exactly what the conditions are on getting a geometry out of it. And there are a few cases where there are a few particular observables, including the one I'll talk about today, which is the torus in 2D CFT, where we understand in complete detail what that means and what the necessary and sufficient conditions are, but mostly it's more vague. Mostly it's not pinned down so well.
And sorry, you should go on, but in terms of our definition of what emergent geometry would be, would it mean, for example, that the boundary correlators for the stress energy tensor would agree with what you would get from pure Einstein gravity, or would we allow for higher derivative corrections? I mean, what exactly would we mean by emergent geometry?
I mean in particular that there's a limit that is Einstein gravity plus a few matter fields in the bulk, and that's the limit we're going to be aiming for. Okay, so the first part. The first part of these lectures, including all of today, I'm going to talk about 3D gravity and two-dimensional CFT. So in 3D gravity, the action is the Einstein action plus some matter fields. An important simplification, in fact, sort of the whole reason that 2D gravity is so much easier than higher dimensions is that this is effectively the only action for gravity in 3 dimensions. There are no propagating degrees of freedom, but gravity still does play an important role. But it's important that there are no non-trivial higher curvature corrections that you can write here. Well, you can write them, but then you can eliminate them by a field redefinition. So there really is not any such thing as curvature corrections in 3D gravity. The Einstein action is unique. And this is dual to the 2D CFT with central charge C equals 3L over 2G Newton. So this is basically the ADS length, LADS, over the Planck length, which, in order to make sense of this theory semi-classically, had better be much bigger than 1. So the semi-classical expansion in the bulk is the large central charge expansion. And this central charge in 2D CFT sort of plays this role of the number of degrees of freedom. Certainly it's a necessary condition for holographic CFTs to have large central charge.
Right. The fact that you can eliminate all other terms, this is this on-shell kind of equivalence. Right? I mean, the fact that on-shell all metrics are ADS, and that results in this possibility. Is this right? The field,
yes.
Field redefinitions
That's right.
produce equations of motion.
That's right. Yeah. It's almost easier to think about from the CFT point of view. From the CFT point of view, the only set of correlation functions you can have for the stress tensors are the ones you get from the Virasoro algebra. The Virasoro algebra is unique up to the central charge, so there can't possibly be other theories of gravity that you could stick here with some other parameters. So this is the semi-classical limit is c much greater than 1, and as I said, that sort of plays the role of the number of degrees of freedom. There are various ways to calculate this. There are various ways to define the central charge. I'm not really going to be talking about Virasoro, so for our purposes, maybe I'll just define the central charge to be the Casimir energy of the vacuum state. So there are various ways to do this. It shows up in the TT two-point function, the Virasoro algebra, but this is the only one that we'll need. So what I'm going to talk about today is the spectrum of 3D gravity. So the plan is to understand the spectrum of gravity and to understand how that comes from the CFT and what this universality class of holographic CFTs is and how it's responsible for the spectrum of 3D gravity. This is mathematically, this is a really simple example, and that's why I'm giving this example first, because this is one where we can just calculate all of the conditions from conformal invariance. I can do all the calculations on the board in 3 lines. So it's pretty simple, but the main idea that goes into this is exactly the same as what's going to be responsible for much more intricate things that I'll describe without quite too many details. So the density of states is e to the s. And what we would like to know is the entropy at order C. So we'd like to know all the order C contributions to the entropy of 3D gravity. And from the gravity point of view, that's easy. So the order C contributions to the entropy come from the Bekenstein-Hawking entropy area over 4G Newton. So the order C contributions to the entropy from the gravity point of view are just the classical, so just all we need to do is find all of the classical solutions with horizons. So we just need to enumerate all the black holes of 3D gravity, and from there we can read off the entropy at order C.
When you say order C, you mean you make E order C and J order C, and then you want the S order C.
Correct. Yeah. Okay, so
E order C, J order C.
J order C.
okay, so I'm going to start keeping track of the spectrum on this plot here. So this is the energy spectrum. We said that the vacuum is sitting here at E is equal to minus C over 12. It's the Casimir energy. A note of notation here is that my definition of energy is scaling dimension minus C over 12. I'll just be using energies to keep track of the spectrum. Okay, so we need to start cataloging the black hole solutions. The easy ones to write down are the ones that are universal to all theories. So these are the ones with the matter fields turned off. And we're not talking about pure gravity here, we're talking about real theories of quantum gravity in ADS3. So there are lots of matter fields around, and there are lots of different black hole solutions. But the simplest ones are BTZ. So the BTZ black holes, by cosmic censorship, have E greater than or equal to the absolute value of J, which obviously is bigger than 0. So on our plot of the spectrum here, there's a gap. The vacuum is at minus C over 12, and the first BTZ black holes start at E equals 0. The BTZ has entropy S equals 2 pi root CE over 3. So these solutions give that contribution to the entropy. It's hard to imagine theories of 3D gravity that don't have BTZ black holes. I don't know if it's impossible to imagine them. I mean, the reason it's hard is that BTZ is just a quotient of empty ADS. So everything that has an ADS solution seems like it ought to have this quotient solution. Now, I don't know if that's completely solid because you could imagine instabilities from the quotient. I don't know of any case where that happens. All the situations that we know of do have all of the BTZ black holes, but I'm not sure whether, especially these small ones, perhaps could be unstable in some exotic theories that you could cook up.
So here, E would be order C. Like, what do you mean by it starts from 0? S should be, E should be order C.
0 times C. Yeah. In the sense that it's not that there's nothing. Yeah, maybe I should say that this is what I'll call the gap. It's not that there's nothing in the gap. There can be lots of stuff in the gap, but there are no classical, at least down here, there are no classical solutions at the horizons. There can be like gas of particles, which contribute to the density of states here. But those don't show up on our plot because we're only keeping track of order C.
Sorry, can you just explain once more? So I thought here you wanted entropy of the order of C, right?
Yeah.
So E should be C times some number which is finite, right? It should not go as 1 over C.
That's true. Yeah.
So what exactly you mean by BTZ starts from, but I would only look for solutions which are a bit far from 0 as well, right? Is it?
Well, 0 really means 0 within the resolution of only keeping track of order C stuff.
You can draw the diagram of
Yeah.
E by C.
Yeah. Okay, so those are always there. Now, that's not all. There can also be exotic black holes or black objects. And these, by exotic, I mean these are black holes with the matter fields turned on. Okay, so these certainly exist. They have shown up. They showed up in the string theory literature under the name of the entropy enigma, because there was some puzzle about matching the entropy of these solutions. But the important thing here is that these exotic black hole solutions will depend on the theory. We know that because we know in examples. So if you take M theory on a Calabi-Yau, you get one Calabi-Yau times a sphere. You get one set of exotic black hole solutions. In that case, what can happen is that you can get black holes that are localized on the internal space. Now, when you interpret that as a black hole in the three-dimensional solution, it's some black hole with matter fields turned on. A different situation is you can take 2B on T4 times S3. In that theory, you get a different set of exotic black holes. In that theory, what can happen is that you get multi-center solutions. And those give you multi-center solutions in 3 dimensions with matter fields again. Okay, so these depend on the theory. Their entropy depends on the theory. The density of states that you get depends on the theory. But a observational fact is that
The multi-centered all lie within ADS3. That is, there's a single ADS3 which contains. Is it?
yeah, that's right. These can be viewed as 3-dimensional. These can be viewed as solutions in the ADS3 theory. Yeah.
And the guys that are localized on the sphere would involve an infinite number of charged fields from the ADS3 point of view, right?
Turned on?
Yes.
Yeah, that's.
Because each of the Fourier modes would have to be turned on to get some. Or not.
Yeah, that sounds right. That sounds right. Yeah.
Is this kind of hair associated with breaking of some symmetries, or this is other more exotic? Okay, never mind.
Not that I know of.
But in the case of the sphere, it would be breaking of that rotational symmetry.
Rotational, yeah, that's
Oh, right. Yeah. Yeah.
Yeah, so in that case, perhaps it's.
I think that would be a standard superconducting kind of instability, but with many charged fields.
Right. Okay, so we might get concerned at this point that we're never going to be able to say anything universal because we didn't say whether we're doing 2B or M theory or what the internal space was or so on. But an interesting fact is that these exotic black hole solutions have entropy greater than the BTZ only at low enough energy. Okay, so how low is low enough depends on the theory, depends on the details. But in all known examples, the transition from the exotic regime to the BTZ regime is well below C/12. Okay, so these exotic black holes sort of exist in some range like this. That can go below 0, but ends before C/12. Okay, so the story in 3D gravity is that below the threshold for the exotic solutions, it's just empty up to field theory stuff. You can have gas and particles, boundary gravitons, that sort of thing, but otherwise it's just empty. So there's this gap. Then you have a regime that's non-universal, that's governed by the details of your theory, where you have exotic black holes, and these control the entropy. So the entropy in this range is theory dependent. And then at some point, the entropy of the BTZ becomes larger. So above here, the entropy of the theory is just 2 pi root CE over 3. This gap is what I was referring to, and I'll call having a sparse spectrum. So it's just the statement that there can't be too many states with energies well below C.
And the exotic solutions go below energy 0.
Yeah, they do. Yeah. Or they can. I don't know if they always do. Yeah. So this sparse spectrum is just a basic requirement for a theory to be holographic because you want the bulk theory at low energies to have some finite number of fields. You don't want order 1 over g Newton number of fields in the low energy theory. In specific examples, like in gauge theories, this is related to the strong coupling of the gauge theory. So it comes from tuning up the coupling constant. From the sort of Bootstrap point of view, we don't really think about it this way. We just think about it as a fact about the spectrum that we input. The dynamics of where that sparse spectrum came from, this is also a really important question. This is something you, as far as I know, have to study gauge theory to understand. I don't know really any more universal way of understanding where large gaps come from, other than looking at examples. Okay.
So this exotic thing, is it an example by example that people have seen, or is there a general proof that they are always?
It's example by example, but I'll give a general proof now. It was example by example. Okay, so that's the spectrum. Anything that we can say about the spectrum, we could restate in terms of the free energy. So let me describe the calculation of the free energy in 3D gravity. The partition function as a function of beta is, in principle, a path integral in the three-dimensional theory. You can approximate this by a sum over saddles. The simplest saddles are, well, let me write them first, and then I can explain what they are. There's one with action beta c over 12, and there's one with action 4 pi squared over beta c over 12. And then there are the saddles corresponding to the exotic solutions. So the first one here is thermal ADS. This is a Euclidean solution which you get by taking, so we're calculating the partition function at finite temperature. So this is, from a CFT point of view, is a partition function on a torus, or so the path integral on a torus. So we need to find saddles that have torus boundary. The first one is one where you fill in, where you make a solid, so this is the boundary torus, but you're going to fill in this torus by filling in, let's see, for thermal ADS, we fill in the, wait, I got this backwards. For thermal ADS, we fill in the space direction. Right, okay, yeah, I wrote it backwards in my notes. So we fill in the angular direction, and the Euclidean time direction is just a trivial S1. The BTZ solution is the other way around, so the solution looks the same, except now we're filling in the Euclidean time direction, and space is a non-trivial S1. Okay, so the actions here come from, the exponents here coming from evaluating the on-shell action for these Euclidean solutions in 3D gravity. There's no matter fields turned on, so this is just the universal piece. This is the part coming from the fact that every theory presumably has BTZ black holes. Now, we might worry about the exotics, but another fact, a related fact about the exotic solutions, is that exotic black holes never dominate over these. The exotic black holes never contribute to the free energy. They contribute to the entropy in the microcanonical ensemble. They have bigger entropy than BTZ for this range here. But when you work in the canonical ensemble, the exotic solutions are always invisible. And this, again, is an observational fact about the examples that we know, that you just don't see them here.
Suppose you left out the thermal ADS. You just
Yeah.
compared BTZ with the exotics.
Uh-huh.
Then presumably the exotics would start dominating at low enough temperatures.
Mm-hmm.
But it's just that where they dominate, thermal ADS is more dominant.
That's right. Yeah. So you could try to tune the temperature down. As you tune the temperature down, the canonical saddle point is going to fall lower and lower. But instead of going down here and probing these black holes, as soon as you get to there, the saddle point jumps to there. So you never see anything in between.
And then, of course, the other filling-ins of the torus, but they're also silent.
Yeah, that's right. Those are never dominant in Euclidean signature. Yeah.
So just to make sure, the exotics do appear as saddle points, is it?
Yes.
But, then they lose out to one of the other.
That's right. And that bound, like, that's only true because their action is never too big. There's some upper bound on what the action could be for that to be true, and you could go and calculate the action of these exotics, and they never surpass that bound.
It sort of makes intuitive sense. You expect them only to be important at low temperatures, but then from modular invariance, they would also have to be important at high temperatures. So better than never be important. At least.
You mean thermal ADS becomes at high temperature the BTC?
Yeah. So they would have to have an analog. Yes.
There could be an intermediate range where they're self-dual.
Yeah,
they're
exactly.
Here and there,
Exactly.
and not here and there.
If they had a big enough action,
Right.
you can imagine, if they had a big enough action, you can imagine a range like this
Right.
where they contributed. Yeah. But I don't think that ever happens.
So you're saying instead of going to temperature 2 pi or 1 over 2 pi, you could have a transition first to this exotic
Yeah.
and then to the
Right.
That would be reasonable. Yes.
Right.
So you probably mentioned this, but how low can the energy of this exotic be? Like,
How sorry?
how low can the energy be? Like,
Oh, I don't know. I mean, it can't go down. It can't. There's always some finite threshold for where the exotics start, and it can be below 0, but I don't remember beyond that.
what determines this threshold? Like how low the energy is?
What determines it? It's just some order 1 number times c, but I don't remember the number.
And you're going to give us a proof that these exotics will never dominate. Have you learned something?
Yeah, that's right. Although there's assumptions in the proof, and it does allow a loophole for the case we just said, where if it was self-dual and large enough down here, then you could do it. But you would need, but it's a very weak assumption from the point of view of the spectrum. What you would need, if you wanted to get this to work, what you would need is exotic solutions with entropy bigger than the symmetrical orbifold theory. So that's very hard to imagine getting from a microscopic point of view. Usually we start with the symmetric orbifold, we deform it, and everything sort of moves up in the spectrum. I don't know how you could make it move down, but that'll be a loophole. Okay, so.
So, can you explain once? Like you said, the canonical ensemble, they really do not contribute at all. Their contribution is.
Well, it's always subdominant to these other 2 saddles. That's the statement. It's exponentially large, but it's not as big as these. So if we take the log of that, then well, taking the log of the sum of exponentials is the same as just taking the maximum. So there are 2 phases here. There's a phase at low temperatures, which is the vacuum phase. There's a phase at high temperatures. Which is the black hole phase. And as we were just discussing in words, the point is that the black hole phase corresponds only to large enough black holes. So this is a version of what's called the Hawking-Page phase transition. The transition happens at temperature 2 pi, and the point is that the BTZs that we were putting on this plot here have 2 types. They have small, unstable BTZs, and they have large, stable BTZs.
What do you mean by unstable?
By unstable, I just mean in the canonical ensemble. I don't mean any dynamic. There's no problem dynamically. If you work at fixed energy, these black holes could be perfectly stable. But if you work in the canonical ensemble, you will find yourself trying to bubble from here to thermal ADS.
In the canonical. But
Yeah.
they don't have negative specific heat.
Correct.
They're just a subdominant side.
Yeah.
That's right. Yeah.
Just to distinguish this from higher dimension, where at some point, in ADS5, black holes, when you make them small enough, Actually, they were negative specifically.
Right, yeah, it's not that. It's not that.
See, I mean, so just to say again, as a saddle point, it would be locally stable.
Correct. Yeah.
In high dimensions, these things, as Euclidean saddle points, become locally unstable.
Right.
There's some negative more.
Oh, yeah.
Yeah. Yeah. Okay, so now I want to explain where this comes from in CFT, basically to derive this directly from CFT and understand when it's true and what the class of theories are that we're talking about here. So the claim is simple. It's that a CFT has the partition function that we just found, this sum of the two exponentials, I should say approximately. We're just talking about the leading order C terms here. If and only if C is much bigger than 1 and rho of E is less than or equal to e to the 2 pi e plus c over 12 for e less than 0. So these are the two conditions that I said are sort of responsible for the class of holographic CFTs. Large number of degrees of freedom and sparse spectrum. This is telling you how sparse is sparse. What do you really need to be true to get a theory that has holographic thermodynamics? This number, this entropy that's showing up here is an interesting entropy because this is equal to the density of states in the symmetric orbifold CFT. The symmetric orbifold CFT is the two-dimensional analog of like free n equals 4 super-Yang Mills. The gravity dual is some point very far away in moduli space in the same theory, tuned to strong coupling. The symmetric orbifold is the weakly coupled version of the holographic theory, which would be presumably dual to some kind of very stringy theory in ADS3.
Sorry, you said this, but so this is the statement of sparseness, that you go from weak to strong coupling and density of states should be much smaller.
It's the condition that the low temperature phase makes sense all the way to the all the way to the transition temperature.
Yes, it's the same as that. That's right.
What I wanted to ask. I mean, but sorry, E plus C, no, sorry, just go ahead and say that.
State vacuum ADS, thermal ADS,
Right.
is its partition function well defined at a finite at temperature up to 1 by 2 pi. That would be true if this was the case.
You mean it would dominate
Yeah.
the
Thermal ADS would have a divergent partition function if this inequality was not satisfied at some temperature below 1 by 2 pi. Right, because rho of
Right.
E tends to the power minus beta.
That's right. That's right. Yeah.
You take e to the beta e,
E to the power minus
times
beta
e
e
to the
times-
minus beta e, and then it diverges.
This, yes. You want the exponential damping to beat the
Another way of saying is if you drop everything above 0, then the thermal ADS dominates the low stuff. That's another way to say it.
Yeah.
You're making it agree with this first line,
Sorry?
this first phase,
What about it?
this beta C over 12, the free energy being that for beta greater than 2 pi.
What was the question?
No, I'm saying that condition is equivalent to the fact that the free energy for beta greater than 2 pi is beta C over 12.
That might depend. I don't think so. No, because this is only a statement about the low energy spectrum. Notice that this restriction is only for energies less than 0. Yeah. Okay, so
So are you ruling out the exotics by definition? of what you mean by gravity?
Ruling out what by definition?
The exotic black holes?
No. So the exotic black holes satisfy this condition.
I see.
Because the exotic, so if we start in the symmetric orbifold theory, and we want to, this is the microscopic dual to the exotic black holes in some particular example, depending on which symmetric orbifold we pick. So if we start at the symmetric orbifold, we start with this density of states. Now we move in moduli space towards the actual holographic theory with the exotic black holes, and that density of states only goes down. So it'll satisfy this bound.
I see.
Okay, so this is derived by modular invariance or modular bootstrap, which is the statement that the partition function is invariant under inverting the temperature, beta to 4 pi squared over beta. And it's simple enough that I can write up the whole argument.
Sorry, can I rephrase my question?
Yeah.
So this definition that your claim that Z CFT equals Z gravity if this holds, that rules out the possibility of exotic black holes ever dominating the family balance.
That's right. That's right. That's eliminated by assumption. It's
I see.
yeah. It's possible that there are very strange theories where that doesn't hold.
Sorry, what do you mean it's eliminated by assumption? You're saying you're proving it provided this is true.
Well, if there are exotic black holes that dominate below 0,
Yes.
so I'm assuming that there are no exotic black holes that dominate below 0.
Where have you assumed that?
Well, this restriction on the spectrum is equivalent to saying that at low enough temperatures, the light partition function is dominated by vacuum.
I didn't quite understand that. It seems to me that that assumption is equivalent to saying that the vacuum is well defined. But how do you know that there isn't some more dominant solution?
So this assumption is equivalent to saying that the sum over E less than 0,
Yes.
e to the minus beta E, is equal to e to the minus beta E vac.
Okay.
These two conditions are equivalent.
So in other words, the
For beta greater than 2 pi.
So sorry, just to ask it again, thermal ADS would give you this density of states, e to the 2 pi e plus c over 12. Is that
No, this is Hagedorn. So this is a much higher density of states than a holographic theory in the gravity regime.
So then, I see. Then I see. So thermal ADS. So this is just the vacuum contribution.
No, it's excitations around excitations around the vacuum, but including all these all these high twist fields that would get very high energies in the gravity.
That's right. So this is very sparse compared to like a bunch of copies of a free field, but very dense spectrum compared to actual holographic theories in ADS3. It's partly in between. It's sitting at the free point in moduli space.
I see. But then I didn't understand Ashok's comment because so you had thermal ADS, then you had the exotics, and you're saying thermal ADS will win out over the exotics for E less than say 0. Doesn't that mean there are more, that the entropy is bigger for thermal ADS compared to exotics
Well, this is only at low enough temperatures.
at low enough temperatures?
So yeah, so I mean the entropy of thermal ADS is 0, but
That's something I haven't understood also after you mentioned it.
Yeah. Okay, but so then why do the exotics lose out because the free energy, let's say, is whichever way it goes lower for thermal ADS? Is that right?
I think that's the same.
Yeah, okay.
Maybe I can. It's a related question.
Okay, go
I
ahead.
don't understand how you can how it can be, you can see that for beta greater than 2 pi, there isn't some other phase unless you control the spectrum at all energies. Why couldn't there be some?
Well, that'll prove. That'll prove. So the assumption,
because of modular.
yeah, modular invariance, yeah. The assumption will only come in at low energies, but
I see.
yeah. So the idea is similar to the Carty formula, and let me quickly derive the Carty formula in one line as a warm-up. So the Carty formula is a universal entropy at high energies or a universal free energy at high temperatures in a two-dimensional CFT. So the argument for the Carty formula is just the following. If you calculate the partition function as the beta goes to 0, so high temperatures, and you do this in the dual channel. So you write this not as e to the minus beta e, but as e to the minus 4 pi squared over beta e. Then, since we're taking beta to 0, this dual temperature is going to infinity and landing just on the vacuum state. So that's e to the minus 4 pi squared over beta times the vacuum, sorry, no sum. E to the minus 4 pi squared over beta times the vacuum energy, which is the Casimir energy, minus c over 12. So the vacuum dominates, or rather the dual vacuum, really. And then we get log z is pi squared c over 3 beta as beta goes to 0. And that is the Carty formula. It's often stated in terms of the entropy. You can translate this into the microcanonical ensemble, but we could just say it this way. And this argument was completely general. I'm just taking the partition function, taking a limit where it projects onto the vacuum, and there's no assumptions that go into that. This is true in any CFT, and so the free energy is completely universal at high temperatures, or the entropy at high energies. Now, let's see. What is here? So this reproduces the BTZ entropy at high enough energy, and this was noticed by Strominger pretty soon after ADS CFT. But it is not enough to reproduce I meant to keep that. I meant to keep my spectrum of ADS3 around. Okay, maybe we'll put it back later. But it's not enough to reproduce that picture, because there we didn't just learn the free energy at very high temperatures. We learned the free energy all the way down to 2 pi. Okay, I'm going to put it back. Right, so in this picture of the spectrum of 3D gravity, we knew the free energy all the way down to here. So where does that come from? And the answer is this other set of assumptions. And the point is that in theories with these assumptions, large C in a sparse spectrum, the Carty regime extends all the way down to low energies, all the way down to the black hole threshold. So the way that this argument goes is also by modular invariance. But instead of studying modular invariance in the limit beta goes to 0, we can study the same equation in the limit c goes to infinity. you go through, maybe I'll skip the algebra, but if you go through a similar three-line argument, working in the limit c goes to infinity, then what you find is that z of beta is equal to the sum of the negative energy states e to the minus beta e plus the negative energy states e to the minus 4 pi squared over beta e.
So in the limit c goes to infinity, z of beta is just, you can write it in terms of e less than 0. But
That's right. Yeah, basically what's happened is that you can rewrite the heavy states in one channel in terms of the light stuff in the other channel. And so far, I've only assumed c goes to infinity. Now, we had this other assumption that about the low energy spectrum. And now that the partition function has just been reduced to all low energy stuff, you can use this assumption about sparseness to see that if the theory is also sparse, then these sums are just dominated by the vacuum term. Okay, so if it's sparse, then the vacuum state dominates these sums.
sparseness was again that statement rho of e is less than, is that right?
Yeah, that's right. And you find z of beta is given by e to the beta c over 12 plus e to the 4 pi squared over beta c over 12, which is the partition function for 3D gravity that we wrote up earlier. So this simple set of assumptions is enough to get this universal behavior in the partition function.
So when did you use this rho was given by some?
That's here. That was what I meant here. This is the bound on rho of e for e less than 0.
That would imply the null vacuum.
Yeah, that is enough to tell you that you can just replace these sums by their leading term.
But what I was asking, like, how do you get that? I could have got something else. Like, what was the principle? Did you, like, why did you write that particular combination?
Because it was, well, you mean why did I make that assumption as opposed to some other assumption?
Yeah.
It was so that I could get from here to there. I mean, the goal was to understand what are the necessary and sufficient conditions to get gravity answers out. And so once you get to here, you can see that that's what's needed.
Sorry, Tom, I'm being very stupid, but I can't see this to that.
Yeah, I mean it's a couple lines. I could do it, but maybe it'd be more. I could do more interesting stuff if I don't do it.
Okay, but just very roughly, Z is the sum over all energy states. So the first term there looks like half of the first term there.
Yeah.
And the second term there looks like half of the second term there,
Yeah.
except it has the wrong sign.
Yeah. So what's happened here is that this has a light and a heavy term. This has a light and a heavy term. And in the large C limit, the equations basically decouple, and you find that the light of this is equal to the heavy of that,
I see.
and the heavy of this is equal to the light of that.
I see.
That's the way the argument goes.
Okay, thank you.
Okay, so to summarize, in a general CFT, the Carty formula holds it at high temperatures or high energies. But in a holographic CFT, with these assumptions that I laid out, the regime goes all the way down to C over 12. So some comments. this fixes the energy S of E to be equal to the Carty energy, sorry, the entropy, Carty entropy.
I understand that just the statement of sparseness proves that exotics never dominate, right? Because it's just the sum of these two. You're not getting any contribution.
Right, yeah, there's nothing else. That's right.
Okay.
Yeah.
That wasn't obvious when it showed
Yeah.
you at that exchange. Okay, now I understand.
Yeah.
All right, thank you.
So this fixes the Carty entropy for E greater than C over 12. And it also tells you exactly, well, it reproduces exactly what we saw about these exotics. It tells us that the exotics range E less than C over 12 is non-universal. But they can't dominate the partition function in the canonical ensemble. So we just got the thermal ADS and the BTZ saddle. We didn't get any exotics.
Tom, I didn't quite understand why was that gravity and just two pieces and why not just symmetrize over all SL2Z images?
The other SL2Z black holes are never dominant in. Yeah, that's right. Yeah. Yeah.
I suppose they could become dominant if you turn on rotation capital potential.
Yeah, I think in Euclidean, I think the statement is, if I remember, that in Euclidean signature, so like with imaginary angular potential, they're just never dominant.
Well, I mean, if you turn on an imaginary chemical potential, you can continuously go from this to that. And then this will be subdominant compared to this. So at some point there's going to be a transition. If you just twist the torus, tilt the torus,
Yeah.
at some point you're going to make the tau will go to tau plus 1. So
Yeah.
what you were following can't continue to become. It's not a very important discussion, but I just think what you just said can't be right. Unless it was extra.
Okay, maybe we can look at it. I think I think they can't dominate, but okay. I don't remember the formula though. Okay, so different UV completions can have different entropy in this range, but that's fine. We understand that non-universality from CFT, and we've understood why it's always why it is universal above C over 12. So there's an open question here that I think is an important one, so I want to discuss for a few minutes, which is, do all CFTs have a primary with E less than C over 12? So far, I've just been talking about the leading terms in the partition function. And the leading terms came from the vacuum and stuff at C over 12 and above. Now I'm asking a question about the subleading terms. I'm still at large C, but I'm asking whether those subleading BTZs actually exist or not. From the gravity point of view, it seems like they do. From the gravity point of view, BTZs start at E equals 0. So from if all theories of gravity have BTZ black holes, then we expect that Carty spectrum in the microcanonical entropy, there's no problem with talking about these small black holes. And we expect the Carty entropy to extend all the way down to 0. Now maybe there's also contributions from exotic black holes, But at the very least, we should have the contribution from BTZ. But this turns out to be a really difficult question to answer because it's a question about the subleading terms. There have been some attempts really the only way that I know of trying to answer this question is by numerical bootstrap. Numerical, maybe I should sort of put in quotes, it's the method that's called numerical bootstrap. You don't necessarily have to do it numerically. The original works on numerical modular bootstrap were not really done numerically. This is work by Hellerman, and he derived bounds analytically. But it's the same method that people put on computers. And what they do is they write the crossing equation, or in this context, this modular invariance equation, z minus z equals 0. And they apply linear functionals to that equation and try to rule out CFT spectra. Okay, so often this is discussed for 4-point functions. It's been used to great effect in the 3D Ising model. But you can apply it to partition functions, and you can rule out, or you can try to rule out, some guess for a CFT spectrum. So in the limit C to infinity, Hellerman studied this problem analytically and found the bound that the energy of the first primary in the large C limit has to be less than or equal to C over 12 plus some order 1 constant that he calculated. That was done analytically. I think most people who thought about 3D gravity and thought about this question would have said that the bound should be E goes all the way down to 0, just because of the BTZ black holes. But we really haven't managed to get past C over 12. There's some intriguing work, first by Keller and Friedan, and then by Collier, Lin, and Yin, where they study this numerically. So this work of Hellerman was just using very simple functionals at low orders. If you want to try to get a better bound, you really have to put it on a computer. But the problem is that when you put it on a computer, you have a competition between how big the central charge is and how hard the calculation is. Okay, so the bigger the central charge, the harder the calculation on the computer. So people have gone up to moderate central charges. The sort of state of the art is around 150 or so. This is by Collier, Lin, and Yin, and they found E1. They found a bound on E1, which is roughly around C over 10. Okay, and it very well could be that if you could push up the bootstrap higher and higher, really to large central charge, asymptotically large central charge, that you might be able to do this. The problem is just that this basically the difficulty of this calculation grows as c to the 5th power. Okay, so you can imagine what happens when you try to make c bigger. We've been trying to develop new techniques to do this recently, and can push this up now to around c is 2000. And we have a bound that I don't think anybody was putting their money on this one, but it seems to be possibly converging to c over 9. Okay, so we got 9.002 is the latest number that we're able to get. And I don't know if that's just a coincidence at c is a few thousand, or if it's really converging. But that's in here somewhere. I don't really know what to make of that. So
I'm really sorry, I'm missing something. C over 12 is a smaller number than C over 9, right?
Oh, sorry, this
How
is
are we
delta.
doing better?
Sorry.
We didn't repeat it.
No, what happened is I switched I switched conventions here.
Okay.
This was delta. So I need to subtract C over 12 from these.
Okay, I see.
Yeah, sorry. Thank you. Okay, so this is sort of a messy calculation that you have to do on a computer. Why bother doing this? What's the point? Are we really going to learn anything by doing numerical bootstrap at higher and higher orders? We don't
Sorry,
just.
I still don't understand how that answer.
Oh, what did I? Is it still not working?
But I thought we could write the first answer as C over 6 minus C over 12. And then it's C over 10 minus C over. So you.
Or plus? Maybe I meant plus.
You're
Let's see.
lowering
Delta.
and
Delta is E
you
plus.
want to push that way.
Yeah. No, that was right. That was right.
No, but why is the lower number? The lower number seems. Sandeep's point was the right hand side of the lowest thing is bigger than the right hand side of, let's say, the middle line.
Okay, yeah, that.
Okay. I guess I.
Okay, yeah, that comparison.
Okay. I guess I messed up the number. Let me just erase the number. Lower.
Lowest.
Well, there we go. Yeah. I was thinking in terms of delta. These shifts get annoying. Okay, so what do we learn from doing this? Well, yeah.
Could I ask?
Yeah.
Let's suppose that it was possible
Yeah.
that the saddle point ended at the phase transition part. Then the saddle point would have to become unstable there somehow, right?
That's right.
So now that if the black hole becomes unstable at that point, the thermal ADS also becomes unstable at that point. Because they're the same size.
That's true. Right.
Okay? So it would see, and thermal ADS does become unstable at that temperature, provided rho saturates your bound.
At C over 12, you mean?
Yes.
That's true. Yeah.
So it would suggest that in a theory where that bound is saturated, black holes don't exist below that temperature. Is that right? I'll say it again.
Yes. No. That I think is that. I think that's true, but that won't really help here because this is the first primary. Like we're not just looking for black holes here. We're bounding the first primary, so it can't be a lot of light states to avoid this problem.
Okay, but one question we could ask is how this black hole saddle, how far does it go?
Yeah. Yeah.
Okay, and it seems that it's possible that really ends,
Yes, I think that is possible.
and
Yeah.
perhaps does happen in the symmetric product. Or I mean, before the states are cut off.
Yeah.
So did he mean, so as a solution, the saddle exists all the way down to zero mass BTC?
Yeah, but it could be that it could be
unstable,
unstable. Yeah. Yeah.
And what was your point, Shiva? Let me fully understand what you meant.
Let me say it again. See,
Yeah.
suppose we take the thermal ADS saddle and look at a temperature larger than 1/2 pi.
Okay.
That saddle doesn't make any sense. It's not a question of stable, unstable. It's just meaningless if rho grows faster than 2 pi. Okay, that seems by modular invariance dual to the question of whether the black hole saddle exists at lower temperatures than 1/2 pi.
I'm not sure if that's true because we're talking about subleading terms in the equation for modular invariance. That modular invariance is already at leading order satisfied by the vacuum and the high energy stuff, and I don't know that you can compare subleading terms in the crossing equation because you could be contaminated by what you dropped in the leading terms.
Right. It's possible that it would but suppose it was working saddle point by saddle point.
Yeah.
If modular invariance was
Okay.
exchanging the saddles,
Yeah.
which is the way it does in gravity, right?
Yeah.
Okay, then it would suggest that the black hole at that point would become unstable for beta less than 1 by 2 pi. It would not become unstable, would just not exist. So at least there's something, I mean, and this, as you said, this rho of E is, this growth 2 pi E is actually saturated in the symmetric product of the fold.
Yeah.
So it suggests that that other saddle in the symmetric product of the fold sort of disappears at below 1 by 2 pi. At least it suggests to me. I was just wondering whether that was true for the symmetric product or before, in which case you could probably check it.
In the symmetric orbifold, there are exotic solutions
Before that. Right?
down here. I think maybe the exotics go all the way up to C over 12 in a symmetric orbifold, but I don't quite remember. I'm not sure of that.
Okay.
What would be the implication of that in terms of the spectrum? Like the black hole,
Yeah, but as Tom said, I mean, he was asking a more sophisticated question, whether there's any primary below this. But there's a simpler question one could ask. In large C, does the saddle point that dominates the ensemble for temperatures larger than 1 by 2 pi, does it continue to extend below? Okay, that's a simpler question. If the answer to that is yes, the answer to Tom's question is clearly yes. It's not the other way around. But anyway, that's a simpler question, one that one could more easily imagine answering. Okay, and it sounds like for gravity it's an interesting question, right? Because we're
Yeah.
interested not just about
Yeah.
saddle points, we're interested about black holes.
Yeah. Yeah.
I think what perhaps answer that.
But so, okay, you must go on. Because now I got really confused. I thought the data was that did you mean in the canonical ensemble? Just in the canonical, I thought it was clear it jumped from the BTZ to the thermal.
Yeah.
Okay.
So let's do canonical ensemble, let's fix temperature.
Yes.
And now, as a function of as a suitably undefined order parameter, you can imagine that you have many saddle points. You've got a Landau-Ginzburg kind of potential, there are some maxima, some minima, and the competition is between these various minima.
Okay.
Okay, so at some point you're undergoing a first order fixed transition.
Right.
So you're switching from one minimum to the other.
The other.
But the question that you could ask is, does the minimum continue to exist? It may not be dominant, but does it continue to exist as you go past the temperature?
Yeah.
Or does it,
Yes.
disappear?
Right.
That sounds like an interesting question
Right.
related to your question.
Yes.
And it's, my suggestion is that it will disappear in the symmetric product.
Huh. At C over 12. Is that
Yes.
is that the guess?
Yes.
I think that's quite possible. Yeah. I think it may sort of become the exotic solution.
Yeah, it changes nature.
Yeah. I think that that sounds vaguely familiar. I'm
Okay.
not sure.
And that's just due to the fact that the thermal ADS cannot exist unmodified above Hagedorn temperature,
Uh-huh.
which is an obvious thing.
Yeah.
Okay.
Okay, so I just wanted to make the case that I think this problem, even though it's numerical and it might not be clear what insight we'll gain from doing that numerics harder and harder, but actually I think a lot can be learned from this, and this is worth pushing. And the reason for that is because if you can push this really to its minimum, well, hopefully that's 0, but wherever the minimum is, if you can really work at large C and push E1, work at, run the computer long enough that you can find the optimum here, then you can not only use this to bound the gap, but you can use it to construct or potentially rule out a theory of pure gravity in 3 dimensions. Because when you solve these numerical bootstrap problems, you don't just bound the gap, you get an answer for the spectrum. Okay, so if you can get this to converge towards something that looks like pure 3D gravity, you've also calculated the spectrum of pure 3D gravity. And from there, you could then turn to correlation functions. You could really start probing whether pure gravity exists in 3 dimensions. And this would start to get at some of those questions that I posed at the beginning, like, do we need to add some KK modes and extra dimensions to make sense of pure gravity in 3 dimensions, or can we do it just with gravity? Do we need something that looks like strings? We can start to add matter. For example, we could add a U1 gauge field and answer questions about weak gravity or the swampland. Like, if we add a gauge field, do we have to add charged matter? How heavy can the charged matter be? These are questions that I think we would really like to know the answer to, and ideally we could answer them analytically. But worst case, maybe we can answer them numerically.
What would be the bound on the first primary to rule out the predicated? This is the lower, the upper boundary.
Well, if this were right, so if it went down to here, which I don't think will happen, but if it went down to here, then you would rule out 3D gravity, or
So like that. Okay.
because pure gravity doesn't have anything down here. But what I think is more likely is that you keep pushing this until you get it to go to here, and then you can write down the spectrum of pure gravity in 3 dimensions and start to understand all these subleading terms. Now, analytically, we could really only get a handle on the leading terms at large C, but numerically, you get all the terms. You can ask about subleading saddles. You can ask whether these small BTC black holes exist below the phase transition, questions like that.
And I'm really sorry because I haven't kept track of this whole set of developments, but Witten had proposed that this may be true, and then there was lots of developments ruling things out
Yeah.
and so on. So what has been ruled out in so far as just pure gravity being a consistent thing that for C, that's just for finite C, right? No, sorry, just 2 minutes. And then
Yeah, so Witten proposed a partition function for pure gravity that was holomorphically factorizing into left and right. Then Witten and Maloney calculated the path integral by summing over saddles. And first of all, they didn't get Witten's answer. So it didn't support that conjecture. And secondly, they got an answer that didn't even look like a partition function, because it could not be expanded in in powers of e to the minus beta. So they gave various potential conclusions from that calculation. One of them is that 3D pure gravity just doesn't exist. Another is that we just don't really know how to do the path integral well enough to do the calculation. Or maybe we have to include some other non-perturbative objects. I don't know if then we call it pure gravity or not, but the suggestion was that you couldn't, at least you can't get it by doing the path integral the simplest way. So I think it's just not, I think it's still just an open question, really, whether,
pure
yeah,
gravity
yeah.
exists.
Yeah, there was later work by Maloney and Keller and others showing that some very minor looking modifications of the Maloney-Witten calculation did give something that makes sense. There wasn't really like a first principles reason for doing those modifications, but maybe that's what you're supposed to do.
Witten Maloney answer was the 2 terms that you had written down plus the other images.
That's right. Yeah, the sum over SL2Z.
Dressed with the determinants,
That's right.
which they could compute exactly at finite C
That's right.
because of Virasoro. And then they just asked whether that answer is integers in e to the power minus beta e, and it was.
Yeah.
So
That's right.
it was the 2 terms plus other ways of filling it, is it?
All of
With determinants, always, okay. I see, but that came out of their exact 3D partition function calculation.
Yeah, you can do the partition function over thermal ADS exactly because it's Virasoro, and then you sum over the images. That's basically it. And then you can ask, is that a partition function?
I see,
Is
because
it trace over a Hilbert space? It's not.
okay,
Right.
everything is a quotient of ADS through.
Yeah.
That's all.
Yeah.
Okay.
Yeah.
So I got it.
Yeah.
The coefficients are not
Integers. It's a continuous vector.
small modification that you mentioned.
It just corresponds to adding. So, in the original calculation, they assumed that there was nothing up to C over 12 or C minus 1 over 12. I can't remember which. And what Keller and Maloney did was to add some states very close to C minus 1 over 12, but just below. Like, they added like a couple of states, 6 states, I think. They added 6 states right below here, and then everything made sense. So no, it's not clear whether you're supposed to call that pure gravity or not, but it did suggest that it was that maybe 3D gravity or something very close to pure 3D gravity might make sense. I'll just maybe make one more comment and then we can continue tomorrow. The basic structure that we saw in the partition function was this. We found Z was a sum over channels of the vacuum contribution. So in terms of path integrals, the point here is that we're doing a path integral on a torus. And in a holographic CFT, this is somehow reorganizing into a sum over channels. From a CFT point of view, this is very surprising, because we don't usually sum channels, right? We pick a channel, and we sum the stuff that's running in that channel. Like if I take this torus path integral, and I want to calculate it, then I could pick a channel. Say maybe I cut the path integral here, and I define states on that cut, and I can sum over the states that I can insert the identity here by summing over states, and I sum over the states running around the torus. But we pick a channel and then we sum over states. We don't sum over channels. And what happened for the partition function was this reorganization into a sum over channels. So we're adding. So instead of summing over states in a given channel, we're projecting onto the vacuum here at this cut, and then summing over channels. So the other channel, in this case, being a cut going this way with a vacuum projection. I'm saying it this way just because this is sort of the general lesson that I wanted to extract from this, which then is going to apply to all sorts of other observables that we can calculate both in 3D gravity and in higher dimensional gravity, where the sort of magic of large N CFTs with a sparse spectrum is this reorganization of sum over stuff to sum over channels. And I'll stop there for today and take questions.
Sorry, Tom, I didn't understand your last comment. So are you saying you could write Z as a sum over 2 terms, with both getting contributions E less than 0, but there was the, e to the minus beta E and then e to the minus 1 over beta. Right? Is that what you?
Yeah, that's these 2 terms. Yeah, that's right. So this one is the vacuum, and this one's the dual vacuum. So these were the 2 terms in the thermal ADS and BTZ saddle and bulk language.
Right. No. So then it wasn't just the vacuum. It was a bunch of sum over all E less than 0 states, right?
That's true, but with the sparseness assumption that projected onto just the vacuum. So this gives this is just 2 terms, and this is a leading answer at large C.
I see. But what does channel mean then? Sorry, I didn't fully understand. Is the vacuum contribution, but what does the channel mean? You're not just keeping the vacuum, for example, in the low temperature part, you're not just keeping the vacuum, if I'm right?
I am just, yeah, this in formulas, I really mean this plus this. So this is just the vacuum. So by sum over channels, I mean just the original trace and the S dual of the trace.
But where does the E dependence come in? Sorry. So the answer was e to the minus beta A, where E
Yeah.
And where is that coming in then?
That's at large C, every state other than vacuum is some point. Let's say in the case.
Oh, that's what you're saying. Ah, okay. So it's just the sum of the, is that what you're saying? Yeah.
If it's sparse.
Oh, okay, now I got it. Sorry, I was
Yeah.
just putting it together. I'm with you. Okay, thank you.
And so in this sum, you don't add the other channels. There are infinite number of channels, right? Because you can cut any cycle.
That's correct. So those channels never dominate in the calculation that I was doing today. There are other examples, and I'll give some examples tomorrow where you have to sum an infinite number of channels.
So I presume if you take a twisted tori, those will dominate, right? As Siraj was saying earlier.
Okay, I guess I don't understand this comment. I think there is. You're saying if I take z
Yeah. That effectively
beta
twists the
Yeah.
torus.
theta, yes.
So at some point you're going to make a transition. What if you just follow the up guy as you turn on theta? It's going to go to the
Yeah.
1-1 guy.
That's right.
So at some point, presumably halfway between, there'll be a phase transition.
Yeah.
Yeah, because this partition function is not fully modular invariant, right? It's only beta goes to 1 over beta, that's a symmetry.
Yes, that's right. I think, let's see, maybe what I'm remembering, maybe I remembered this wrong. Maybe what I'm remembering is that the additional SL2Z saddles don't affect the entropy. I mean, we already got the full answer. We already got the full answer for the leading entropy as a function of E and J. Well, I set J to 0 in this talk, but we could have done the same thing as a function of E and J. And I think the other saddles won't appear. But you're right that if we want to allow if we want to allow theta to be large enough, then we would have to also include the other images here. Yeah.
The density of states as a function of J probably would be this theta dependence, right? If that.
Yeah. Well, if you don't need to allow this theta to be very large. If you just want to get you can work in the fundamental domain. So you can already get the entropy without talking about the other saddles.
Any more questions, Sechara?
Questions? No, I think we are fine here.